Like if you're excluding the drains.
I mean, come on.
But you're not building it, right?
No amount of thrust power could like get you past the building.
Okay, kids. Yeah. So, on the lab, hopefully what you'll see is that you got a graph of time, and then you're going to plot, assuming that you kept track of what you were supposed to keep track of, you're going to have the natural log and should be coming down here like this, and then you have your 1 over graph, which should be something coming down like this. And hopefully what you see is that natural log is one that's more linear, okay? Because this should be very much a first order reaction, but you're dealing with real data and equipment, and sometimes things get a little bit wonky. So anyway, so what you should see is that your natural log versus time is your first order. And because this whole thing started with your graph where you had concentration, absorbance here. And then you had concentration here, and that should be a linear function. Because remember, everybody's numbers are different. The only thing I can grade is your work. So make sure that you have shown me, like when I tell you, circle the points on the line of best fit and write down the corresponding X and Y values. Guess what? When I look at your graph, I better see the points that you use to find the slope. Okay? And then the same thing when you do, as Ryan goes up and grabs the slab.
Well, I'm just making sure. I don't want you to be mad at the way you grade.
No, I never get mad when I grade. That would be the first time in 30 years of teaching.
I don't think you've ever
I've
been
personally
happy.
seen you get mad while you grade.
You have seen that, yes.
I've
You have.
seen you get mad like while people just answer questions.
No, I've
Yeah.
seen him get mad at a test. He'll literally look at it and go,
You get this.
Yeah, you did that to my test when I
oh, yeah, he did it to mine too.
Oh!
Yeah, or like he like face palms his head.
Yeah, this is why I have a flat forehead. Okay. Make sure on the slope that you have the correct units. Remember, absorbance has no units. Then you have your concentration on here, and that's in micromolarity, so oddly enough, you can find your slope. So when I did it, my data, I had a slope of around 0.07. Okay, that was an ish. Okay, should be something around there. If you have a slope of like 500, that's bad.
about 400.
No, still not good. And your half-life, mine was around 1,000 seconds. Yours is going to be one value. Make sure on 14 and 15 that you just not have said, oh, human error, or there was a problem with the equipment. What did you guys get for your half-lives?
592.
Yeah, I got about
533.
I can live with that.
Okay.
Live with that? Okay, we're good. As long as I don't get yelled at.
No, because that's so much based upon your slope and
If you round to the nearest thousandth, I got close to what you got.
which is certainly good enough for government work. Okay, so anything you want me to go over, Amanda?
I am not quite sure what you're looking for on 14.
Okay? So here's your graph of absorption and concentration, right? So let's say that you've got all of these points, okay, and they're all linear. And you have one point that's way down here, okay? So think through. So here's your cuvette, and you're shining light through this cuvette, right? Good? Now, to get a point well below that, is more light being absorbed or less light being absorbed than all the other points? That's where you have to start to answer this question. So you have all of these points along here, and you have one data point that's way down here. So is more light being absorbed in the other points, or is less light being absorbed in the other points? Less, okay? So that means there's not as many particles in there to absorb that light, okay? So there's only one of two things that could happen. Either you didn't add enough, you fundamentally you mismeasured, and you didn't put enough of the stock solution in there, okay, which is a real possibility, or you put enough stock solution in there, but maybe there was already water in there that caused it to be more dilute than what it should have been. So either you didn't put enough stock solution in, or there was already water in there that made it too dilute. That's the only thing, that's what you have to think through. It's like, okay, what could have possibly caused that absorption to be less than what it should have been? And that's the only thing that you can do, okay? And then on the other side, if you have a point that's too high, okay, you have a measured concentration that was too high. So in other words, the computer thinks that there wasn't enough light going through. So what's a possible thing that could cause that there wasn't enough light going through? So, okay. Now on that question about the pseudo rate law, on question number 6, okay, make sure that you realize that what we're trying to do is that we're trying to keep this so we're only dependent upon one of these that it won't change. Now, we could change the hydroxide, but then we'd have to mess with pH probes and everything else. So we basically overload it with a very high concentration of hydroxide ions, so that basically doesn't change, so then any changes are only dependent upon changes to that crystal violet. Okay, that's the whole point. All right? Anything else about the lab? Going once, twice, sold. So here's what I want for synthesis. So I want the lab itself, then I want, where's the graphs? Then I want your graphs, and if your graphs are on separate papers, just put whichever one goes, you know, that concentration versus absorbance first, and then the other labs. And then the last thing I want is this sheet that has all your data on it. Okay? So the lab, graphs, data. Okay. I'm going to get some ice out. Give me a second. Okay, so here's the reaction that we're going to do to kind of show how you can shift an equilibrium and stress the system. So I've got cobalt chloride, CoCO2, right? And CoCO2 has kind of a pink color to it. Now, so this is technically a complex ion that has a bunch of water molecules attached to it. And when you go to name this, it's actually like CO, then this was like hexaquo cobalt 2. So when you name complex ions, it has its own like weird set of how you name things. But the whole point of this is that this is going to be a pink color. So if I add hydrochloric acid to it, or a bunch of chloride ions, and that's what I'm going to do, is I'm going to add some hydrochloric acid to it. And the other product that I could have is CoCO4. So this is a blue color, and this is a pink color. So what I'm going to do is that I've just got your basic solution of this, and then I'm going to take some 12 molar hydrochloric acid, which is like concentrated stock solution. I'm going to add that to it. And if I add enough, it's kind of trying to. So we're kind of in that transition phase.
Almost there.
Huh? What'd you say?
Atta boy.
Yeah. Okay. All right. So at this point, we've added this reactant, okay, a bunch of fluoride ions, because this is like very, very concentrated, like 12 molar hydrochloric acid. And then we've shifted it over here to make COCl4. So this dynamic was here, we shifted it over here, and we can tell that because it's turned into a blue color. Now, the next thing I'm going to do is I'm going to add some water to it. Now, water is a product on this side. So if I added a reactant, I shifted it over here. So if I add water, what should happen?
You should shift.
I should be able to shift it back the other side. So we'll add some water to it.
Oh,
That's.
interesting. Chem too.
Okay, you kind of see that barrier where you have the COCl4 down here, but you have the water attached to it up here. Actually, let me pull some of this out. It's getting a little bit full. A little water. Okay, now, the next thing we're going to do is we're going to put it in a hot water bath. So if I take this and put this in the hot water bath, this sometimes takes a little bit. So, because just like chloride is a product, and we added chloride and we shifted it over here, the same thing is going to be true of heat. So heat's a reactant, just like anything else is. So if I add heat to it, I should be able to shift it back where it turns into a blue color. I might have added too much blue. Hold on, I'm going to add a little bit of hydrochloric acid.
Don't do this at home.
Don't do this at home.
Maybe hit it harder.
Especially with the 12 molar hydrochloric
How
acid.
nigh can this up?
You don't think that's a good idea, Bert?
What?
The,
To trust kids with 12 molar hydrochloric acid?
yeah, you don't think so?
No, generally not. I don't trust most adults with 12 molar hydrochloric acid.
Why?
So what you can see is that that bottom is getting warm, okay? And that's starting to shift.
Doesn't make sense. You're gonna die. Jordan got the level below high hot and he had to go get Tom.
I'll get the blue color to it.
I told him not to. Jordan, don't do it, it's hot.
Eventually I'll get through the whole conversation.
Just one.
Ginny just
that's
needs to by
He said it's exactly like that.
Okay, so we added heat to it, right? And so now we have shifted it over here to this side. So if I put it in an ice water bath, what should happen?
Go back.
It should go back.
60
Okay.
feet out.
Won't the glass shatter? I was always
No,
told
it's
to come on.
Pyrex.
There's like a big deal.
Yeah, don't put it in the.
Don't put hot stuff in cold stuff.
It's tough to
Well, it wasn't all that hot.
What's that called?
So basically what we're proving is that if you put a girl in really hot water,
Wait,
A girl?
stop.
yeah, if you put a girl in really hot water.
This actually goes faster than the hot side does.
I look pink now.
Yeah, so I've removed heat, so that shifted us back over here. Right now, here's the last thing we're gonna do, we're gonna add a little bit of hydrochloric acid.
Shift it to blue.
Some types of fish. Or frogs or something.
It's like a gender reveal.
Just keeps going back.
You can change the gender of the baby. with
Yeah.
heat.
No.
Measuring what's going on.
Yes, so if you put
Acid and
Okay.
heat.
put a girl in really hot acid,
So
Tape.
now I'm
That
gonna
was
add some
stupid.
silver nitrate to it. Okay? So here's the question. When I add silver nitrate to it, what's gonna happen to the amount of free chloride ions?
They're gonna go down.
decrease.
Why?
Because the AG wants the chloride.
Is silver chloride soluble or insoluble?
Insoluble.
Insoluble. All chlorides are soluble except for
Silver chloride.
silver, lead, and sometimes mercury. Okay? So, going to
I knew that. I saw a video of someone playing national anthem out there.
You could do
so
it.
add a little bit of
A PPT.
ooh.
It's lavender.
So it made a nice precipitate of
Silver chloride.
silver chloride.
It's like disgusting. That looks gross.
It's not the best looking thing.
Oh.
Oh, completely overloaded. And now we've made a milkshake.
Yeah.
So,
Bird.
yeah.
He said, yeah.
Yeah, well, I'm just saying. We just made a whole nice Okay, so here's the drill. So, and notice that this has turned blue, right? So here's what we've got, is that, here's what I want you to see. This is going to be important even like with gas laws. If you add a reactant, it shifts it over here. If you add a product, it's going to shift it back. If you remove a reactant, it has that same effect, right? So if I removed heat, it shifted it back over here. Got the idea?
Yeah.
Okay, back we go.
Head back, fellas.
No. Pocket edition. Like Java edition, just like sit down at a computer, you want to pocket edition, you just take them. I've never heard of pocket edition. Well, I have. I can
Thank you. Okay, so similar type idea, but applied to like it's to a gas phase, all right? So let's say that you have a 1 liter container, we make it simple, and the only thing inside this container is dinitrogen heteroxide, okay, N2O4, molecular compound, okay, and this is just all gas, right? But over a period of time, it can decompose into nitrogen monoxide and nitrogen trioxide. Now, that isn't nitrate, okay? If it was a nitrate, that would be NO3 with a charge of 1 minus, right? So that isn't nitrates. Those are still just gaseous compounds. So I'm taking one thing of N2O4, and it's just decomposing. So first off, assuming that that's just an elementary step reaction, what's the molecularity of that reaction? Well, there's only one thing that's decomposing. Unimolecular, right? Okay, unimolecular. If it was like 2 N2O4 or oxygen plus N2, then it would be bimolecular. If there was 3 things, it would be termolecular. Okay, right? Most of the ones you're going to run into are bimolecular or unimolecular. So, if this is a single-step reaction, what's the only thing that would determine the rate? Concentration of your N2O4. That's it. There's nothing else. Okay? So if this was an elementary step reaction, it would only be dependent upon your N2O4. So if that's the case, if that was the case, if you were to write the rate law, would it be dependent upon the inverse concentration of N2O4 or the natural log of the concentration of N2O4? Natural log, because it would be first order. Okay? And that's what would produce a linear function. Now, we're going to start this reaction. Okay? And we've got a pressure gauge inside of here in a 1 liter container. And the initial pressure is 1.2 atmospheres. Now, that's a little bit more than what you all are experiencing right now, okay? The pressure inside this room is about 1 atmosphere, okay? So if you were inside this chamber, you would feel a little bit uncomfortable, right? It would be a slightly higher pressure, but not bad, okay? You know what you're used to. So over the period of time, this thing is going to decompose into nitrogen monoxide and nitrogen trioxide. So here's the question. Assuming that the temperature remains constant, what's going to happen to the pressure inside that container? Is it going to increase, decrease, or stay the same?
Stay the same.
How many vote is going to stay the same? Okay? How many vote the pressure is going to decrease? Because it's going to be a decomposition reaction. How about that it's going to increase? Mr. Valentine, why did you vote that it was going to increase?
Because there's going to be twice as many molecules inside of the, there's going to be more bouncing off the walls inside the container.
Okay? Because as this goes, you're going to go from, imagine that you have like a classroom full of Timmies, okay? And the Timmies are hooked up with each other, okay? And they're like joined at the hip, right? They got some Velcro and they're holding them together. And then all of a sudden, some of these Timmies start to decompose, right? So now you're going to have individual Timmies running around, right? And remember, you have to visualize what creates pressure is collisions, okay? So if you have more Timmies running around, you're going to have more collisions, and the pressure is going to go up. Now, eventually this is going to reach a new equilibrium, okay? So you would be told, like for example, at a new equilibrium, the pressure goes up, so the pressure is going to increase. So at some new equilibrium, the pressure goes up to 1.8 atmospheres. Okay? Now, what I want to do is I want to calculate Kp based upon this information, right? So, to calculate Kp, I need three things. I need, at equilibrium, because I'm talking about K, right? I'm talking about K. So at equilibrium, I need the pressure of my NO3, I need the concentration of my NO, and I need the concentration of my N2O4. I've got to have all three things, right? But unfortunately, I don't have any of those. But here's what I do know. If you look at this reaction, where you had N2O4 turning into NO and NO3, right? So that initially started at 1.2 atmospheres, okay, and this is going to be important. The only thing I had in that container initially was N2O4. That was it. So there was no pressure created by the NO and the NO3, okay? It's not there. There's nothing there. So here's what's going to happen. It's the same idea. Here's your rice chart, okay? So how much of that 1.2 atmospheres are you going to lose? X. I'm going to go minus X. Now, this is a 1-to-1 ratio, right? So that's going to be plus X and plus X. So at equilibrium, I'm going to have 1.2 minus X, X, and X, right? Now, I'm going to add up all of these pressures created by the N2O4, created by the NO, created by the NO3, right? I'm going to have all of those. So what are all three of those pressures going to add up to equal?
1.2.
Not 1.2. 1.8, because that was the total pressure at the new equilibrium. So if I take the 1.2 minus X, plus X, plus X, I get 1.8 atmospheres. Now, conveniently, when I take minus X plus X, that goes away, okay? That's just going to cancel each other out. So I get 1.2 plus X equals 1.8. So X, oddly enough, equals 0.6, okay? Now, at this point, what do I know?
The pressure of your NO and NO3.
And can I find, now that I know what X is, can I find the pressure of my N2O4 at equilibrium? Yeah, because that's going to be 1.2 minus 0.6, right? So if I take 1.2, now I know that's 0.6. So that becomes, oddly enough, at equilibrium, this becomes 0.6. X becomes 0.6. And the other one becomes 0.6. Okay? So, at this point, now do I have enough information to calculate Kp? Yes. So remember, that's going to be products over reactants. So I'm going to have 0.6 times 0.6 divided by 0.6, and that oddly enough gets me 0.6. Now, here's the deal. So K is going to equal 0.6. So at equilibrium, that's the magic number, okay? Mother Nature wants 0.6, okay? That's it. Mother Nature wants 0.6. Now, is that number really, really small, kind of close to 0, really, really big?
Pretty big.
Well, it's 0.6, right? It isn't like it's, 5 times 10 to the 23rd or something, right? But here's the point. It is a positive number, right? And it isn't really small. So what that means is that this is actually going to be favored in the forward direction, okay? Now, not by a huge amount, okay? But it is going to be favored in the forward direction. So that's why I'm going to produce a little bit of NO and NO3. Not huge amounts, okay? Because it isn't like the K was like 5 times 10 to the 24th, okay? where K would be really, really, really big. So to get a really, really, if you look at how you calculate this KC, okay, or KP, it's because to make it a really, really big value, these numbers up here would have had to have been really big, so I would have had to produce a lot of product, right? And just ended up with a little bit of reactant. So if that was the case, this pressure would have been a lot bigger number, because if I had produced a whole bunch more of that product, my overall pressure would have been a lot bigger, which means my KP value would have been a lot bigger, okay? So that's what you want to be able to think through and go, okay, well, what would I have to do to produce a bigger K value? Oh, I'd have to produce more product, and hopefully that makes sense, okay? Because if you have a bigger and bigger K value, that means that you're producing more and more of that product, and that forward reaction is more and more favored, okay? Got that idea? Now, at this point, I'm going to inject, now think back through what we just did. I'm going to inject a bunch of nitrogen monoxide into this thing, okay? So let's rewrite this, and let me draw a graph. Okay, so let's talk about what this graph is showing. So, this is important. This is a graph of the reverse rate of the reaction versus time. Okay, the reverse rate of the reaction versus time. So, how do you know that the system's reached equilibrium?
A constant amount of product.
Yeah. The reverse rate is staying the same, right? Okay? Now, initially, my reverse, if you were to actually draw this thing from the beginning, there would be no reverse rate because it was all in the forward direction. So if you were to draw this from the beginning of the reaction, this thing would increase, and then when it reached equilibrium, then it would level off. So this is looking at it after we've reached equilibrium. Okay, if you were to start from the beginning, the reverse rate would start at 0 and it would go up. The forward rate would start high and then it would level off, okay? So I know we've already got this thing at equilibrium. It's already leveled off. Now, at this point, I'm going to take like a syringe and I'm going to inject into that solution a bunch of nitrogen monoxide, okay? So at this point in time, I'm going to overload this system with nitrogen monoxide, okay? So, what do you think is going to happen to the reverse rate? Is it going to increase, decrease, or still remain the same? Mr. Carter, think back to what we just did. I'm going to overload it with product. So what's it going to try and do?
Go back.
Yeah. So what's going to happen to the reverse rate? Is the reverse rate going to increase or decrease? It's going to increase, right? So you're going to see a huge spike in the reverse rate, okay? Because of the fact that you've injected a bunch of NO. If you look at what's going to happen mathematically, right? If you look at what's going to happen mathematically, my KP is going to get really, really, my Q, right? My QP, which is a comparison of KP, my Q is going to get really, really big, okay? Because I'm going to inject a bunch of product into that thing. And when that happens, Mother Nature is going to flip out. She's going to go, oh, this is bad, okay? This is bad. I got too big a number. So mathematically, what's Mother Nature going to do to drop that Q where it's back to equaling the K? What's going to happen to the concentration of your product or of your reactant? It's going to go up. The concentration of your reactants is going to go down. So what's going to happen is that you're going to get a spike, okay? And then eventually, that thing's going to level off, and you're going to establish a new equilibrium, okay? So it's like the system is stressed. This is Le Chatelier's principle. The system is stressed because of the fact that I injected a bunch of product. So it's going to spike up. Then, after a while, that rate's going to level back off because now you're going to establish a new equilibrium. Now, what would happen if I removed nitrogen monoxide? So I threw something in there that would absorb nitrogen monoxide. If I got rid of NO, what would happen to here?
The reverse rate?
Yeah, so your reverse rate would
Down,
spike down, and then it would
level off.
level off again. Okay? So that's what you want to be able to think through. Okay, so let's talk about the test. I'm gonna give you questions about, you have energy diagrams like this. Okay? So let's just go with the complicated one right from the get-go. So what do you call this from here, from this set of reactants to this? What do you call the size of that hump?
Activation.
Yes, that's your activation energy. Okay, that's going to be EA1. That's going to be EA2. Which of these is going to be the faster step? EA1 or EA2? Why? Yeah, it has less of an activation energy. Okay, so there's a lower bar, more kids are going to be able to jump over the bar. Okay, so this is going to be your fastest step. So what do you call those points up there where you're going from A to B?
Transition.
Those are your transition states. The relative maximum if you're a nerd, okay? And then here you have B. So what are you going to call B?
An intermediate.
Intermediate. Now, listen. If you were to make this second reaction a catalyzed reaction, so basically you have A, it's going to make B, B is going to turn into C. This is your slowest step, right? Okay? Because this is your lowest activation energy, so you're going to create a bottleneck of B, right? You're going to make it, you're going to create a bottleneck, then it's going to turn into C. Is the overall reaction positive delta E or negative delta E? Mr. Sheldon.
It's positive.
Positive, because my products end up with a slightly higher energy state than where I started. So is it an endothermic reaction or an exothermic reaction?
Endothermic.
Endothermic, because this would have to absorb energy from the surroundings. If I ended up down here, then it would be exothermic, okay? So if this is the normal reaction, if I want to catalyze the reaction, if I want to catalyze the secondary reaction, is that going to raise the activation energy or lower the activation energy?
Lower.
Lower, okay? So if we could find a way to catalyze that reaction, then it might look something like this. Now, if this is the catalyzed reaction, notice that I've dropped my activation energy, okay? This is what you have to remember. you're going to drop the activation energy. But notice that my overall delta E is still the same. So when you have a catalyzed reaction, it lowers the activation energy. But what should that do to the rate of the reaction?
Increase.
It should make it go faster, okay? Because now you've lowered that activation energy, more molecules are going to be above that threshold. Okay. One of the key things to get. All right, so in terms of equations, if there's an equation that you need that's not on your sheet, I will have it on the front of the test, okay? Like that frequency, like the calculating the number of molecules that are above a certain threshold, okay? If you need that, I will give that to you. If you need that natural log of K1 over K2 equals like E sub A over R times 1 over T1 minus 1 over T2, like basically it's a fancy slope calculation thing. If you need that, I will give that to you, okay? So don't flip out over that. What you do need to know, and this is what's on your equation sheet. So if you look at what's on your equation sheet, they give you these reaction rates like natural log, 1 over whatever, but they don't tell you what's first order and they don't tell you what's second order, okay? They give you a half-life reaction, but they don't tell you if it's 0 order or first order, okay? They just give that to you, all right? So you have to know what those are. I promise you, you're going to have to draw a graph. I'm going to give you a set of data table. And you're going to say, wow, is it natural log? Is it inverse? You're only going to have to do one of those, okay? So, but if you really want to draw that nice, make sure that you bring a ruler so you can draw that graph, okay? You're going to have to know the difference between like the rate law and the integrated rate law. One involves time and the other one doesn't. Okay, and you're going to have to go through that process where, like on that acetone lab, where you cancel things out, define the order of the reaction. Remember, that is a process, okay? It is not just about writing down numbers and going, oh, a miracle happens, and this is what I get, okay? So that is a process. Okay, I'm done. I've got the blank review and the answer key to that review, like I always do, and if you haven't handed in the lab, make sure that I get that. So, there we go.